Okay, guess what? This is one of your last theory videos, and I want to welcome you to it. And I know that we're all happy here about it being the last video. And so I'll give you a little applause sign there. Everybody's excited about it being the last video. As far as I know, I believe it to be the last theory information you will need, and it's been a long, hard road, 20 miles of potholes to watch these videos. I know that. I have to watch Collaborate myself when I do training. Been many times when I was completing my degree, I had to watch these videos and listen to a teacher talk me through a PowerPoint. So a couple of things here before we get started. Since it is the last video, we'll probably be communicating via email from this point on. But your last graded quiz will be Monday, and then I have a battery of about 2 or 3 practice tests for you. They're not really worth any points, but what I need for you to do on these when you get them is I will give you the answer key, but what you need to do is you need to take the test without the answer key and without any help from your notes. And if you do this and then grade it yourself with the answer key, you can find out if you have what it takes to pass this CET test. I'm thinking if you get a 75 or an 80, you're probably most likely 99% going to pass. Now, I would like you to get an 80 or higher, an 80% out of 60 questions for each test. I'm fairly sure that you're going to do okay. And the reason why I'm giving this to you is it does cost $60 to take this test. If you pass the test, when you come in to take it, if you pass it, you will get your money back on the spot because we know that you passed the test on the spot. After you're done, you click submit, and we can tell. If you do not pass the test, we have to pay $60 to the organization. So we're going to use that money that you give us to pay the Electronic Technicians Association. So if you do pass, PTI will foot your bill and we will pay for the $60. If you don't pass, then you will have to submit the $60. So you got to bring a check or cash. As far as I know, we can't accept credit cards. So you know, it's a couple of weeks away or more. Prepare to bring $60 cash or a check. So again, you will get 2 60-point quizzes or tests, and I want you to take those. I'll give you the key. Don't use any notes and don't use the key to take the test. And this can truly give you an indication of how well you are prepared to take it. Now, if you score fairly low, 75 or maybe even a 70 on these practice tests, you can find the correct answers and add those to your test pool and try to study the ones that you missed. So these 2 tests are not really for my benefit or to grade you, but just to see how well you've absorbed the information that we've talked about over the last quarter. So 2 of these tests that you'll take are just like the CET exam. The other one, if I do give it to you, I'm not too sure what we're going to do there because I would like to monitor you while you take that test because it's called a program's outcome test. And normally the teacher has to be watching you when you take it. You're not allowed to actually keep it or the answer key. And what we need that for is for accreditation from our accrediting organization. We're accredited. PTC is accredited by Middle States. We need to show that you're actually mastering a certain minimum skill set as an electronic technician, and this test actually measures that. It's actually good practice for the CET, but the questions are actually a little bit tougher. The ones that I'm worried about you passing are the 2 CET tests, the practice tests. Those are the ones that I really want you to do well on. Okay, so what I need to find out from you is how do you want me to get the practice tests to you? I'm going to put them on Blackboard, but I think they're like 8 or 12 pages each. If you don't mind printing those out, that would be an ideal way for you to get it. Another way is some of you have class on site with Mr. Kanjierski. I was planning on for you guys just to give it to Kanjierski, and he could just give them to you. And then I can post the answers on Blackboard. Another way is I can send it to you in the mail. It's a little bit troublesome for me, but I would actually prefer this, or this. And another way would be for you to pick it up at my desk on the file cabinet behind my chair. I can just put it there if I know that you're coming, and whether I'm there or not, you can actually pick it up. So I need to find out right away, as soon as you can, how do you want to get the practice test? Is it okay in Blackboard? Do you want me to just give you copies of Kanjierski so you don't have to print out 10 or 12 pages? Or would you like me to send it via mail? I can get your address and put it in a PTI mail. It might take you a couple days to get it, but at least you will have them. The other option is if you're on campus at all, you can just pick it up at my desk on my file cabinet that's behind my chair. I'm in the on the 4th floor faculty area. Some of you know where I am there, and I can give it to you there. Now, as far as the actual test night goes, after checking your schedule, we have 3 possible days. Thursday, the 22nd, Tuesday, the 27th, or Thursday, the 29th. I'm leaning towards possibly Tuesday, the 27th, and I haven't heard from any of you as far as being not able to attend certain days or nights. These are actually going to be in the evening, so plan on it to be around 5:30 or 6 o'clock, whatever you want to do, or even a little bit earlier. We recommend that you get there a little bit earlier than the time that you are going to take the test. If you come in late, the ETA rules and regulations require us to close the door. After the test begins, nobody's allowed to enter or leave until you're finished with the test. Also, for the test, bring a TI-30 or a very basic calculator like the one that you've been getting. You're not allowed to use any kind of programming calculators. So anything that you would store a formula in or anything that you can store text in is not going to be permitted, and the proctor will check to see if you have the right kind of calculator. So make sure you're doing your problems with a basic TI-30, not one of those algebra graphing calculators. They are not permitted. So you'll be allowed to use scrap paper, a basic calculator. You have to be there on time, bring $60, and let me know if there's any of these 3 nights that you cannot attend, and I'll make sure it's not one of those 3 nights. Okay, so let's move on to this particular video, which is the last one. And if there are any other videos, if I get a lot of feedback and we need some test coaching or something, maybe I will do that for you for next Tuesday. But right now I'm thinking that this will be the last discussion. It will be your last discussion, so I know that you're very, very happy about that. Yes, you are. Okay. Now, get off that first activity sheet. It's about electric motors and generators. What we'll do here is there are a couple of odds and ends that you will run into on the test that didn't really fall under all the other things that we talked about. And after seeing this test for 15 or 20 years, you see these things that maybe have stuff to do with electronics, maybe do not, but they're not really in other aspects of electronics you studied at PTC. And so I just want to make sure we hit these. Some of the stuff you might know, some of the stuff you may not. So let's go ahead and get started. In one area, you might have 1 or 2 or even 3 questions about electric motors and generators. Well, in general, an electric motor or generator is classified as a rotating machine. And what we mean by that is it uses electricity to generate rotational mechanical motion, or it uses rotational mechanical motion to generate electricity. So a generator actually changes rotational mechanical energy into electricity. That's a type of transducer. Any kind of device that changes energy from one form into another is a transducer. A generator is a kind of transducer that changes mechanical energy into electrical energy. Now, what are the 2 main parts of any DC generator or motor? Well, there's the part that spins, The part that spins is called the armature or the armature, and the part that does not is called the field, sometimes called the field winding. So these are the two parts, the armature, which is the moving part, and the winding, which is the part that is stationary. Okay. Now, a generator is usually used, the word generator is usually used to designate a DC device, a generator. Okay. So whether it's a motor or a generator, the two main parts are armature and field. Now, the interesting thing about a DC generator is it actually is a motor. So if you turn the armature, you will generate electricity. If you put electricity into a motor, it'll turn it into rotational energy. So generators and motors are actually constructed the exact same way, DC devices, and they both are made out of an armature and a winding. Any generator can be a motor, and any motor can be a generator. Now, what is an alternator? Well, an alternator is a generator that is made to produce AC. So we can say AC generator or DC generator, but generally in the field, the word generator is used to describe a DC device, and the word alternator is used to describe an AC device. So those are the big differences in the words. So you can say AC generator, that would be technically correct, but usually an AC generator is called an alternator. Alternating current, generating voltage. Alternator, alternator. It's two words put together in one. Now, in a DC device, it has a special name. The parts have a special name, the armature and the field. But in an alternator, to differentiate between a generator and an alternator, we call those pieces something else. The spinning part in a motor or an AC motor or an alternator, which is AC generator, is called the rotor. The spinning part is called the rotor. The spinning part in a DC is called the armature. The part on the outside that does not move in a DC generator is called the field. In here, it's called the stator. This is the stator, the non-moving part. Stationary. Stator, that's where the word comes from, stator, stationary. Rotor, rotating part. So this causes a lot of confusion in generators because we have different language for AC devices than we do for DC devices. Why? So that when we talk about the DC or AC device, we know which one we're talking about. Okay. Now, how can an alternator be made to generate DC instead of AC? This is a weird question, and I see it once in a while. Be prepared to answer it. And here it is. If I spin a coil over here within the field, here's the spinning part, the rotor. And the rotor is a coil, and the coil is spinning in the field. One side of the coil cuts down through, and it generates the positive alternation. And another, when it comes back around this way, it cuts up through. So in this field right here, let me see if I could draw these. In this field, we have these lines of flux here that are between the magnet. They're in there. And the coil will cut down through this side and then back up this way. So half of a turn, what we find is that as it cuts down through, you generate one alternation here. And then as it comes down through and then back up the other side, because you're cutting through the back side of the flux, it generates the negative alternation. So that's how we get voltage to go positive to negative. The coil cuts down through and then back up the other side. You may recall from first quarter, Lenz and Faraday studied the concepts of electromagnets, and what Faraday said was that a coil cutting through magnetic lines of flux will generate a voltage, and what Lenz said was if you move the coil one way, it generates one polarity. If you pull it back through the same magnetic lines, it'll generate the other polarity. So that's exactly how this device is working. Now, in a alternator, we have something called slip rings. In basic alternator, there's different kinds, but in the basic alternator, we have two slip rings, and there's brushes that rub on the slip rings, and that's how we get the electricity off the coil that's spinning in the field in here, inside of the stator's field. And whenever we have these brushes rubbing on these slip rings, you can get an electrical connection. These brushes and slip rings are a source of wear and tear. They eventually have to be replaced because it's a carbon device rubbing on a ring that is spinning around in a circle. Now, if I wanted to convert this to DC, I would need something that would take this negative alternation and flip it around to a positive alternation. And the way that we can do that is we can take these slip rings and make one collar and then split it into two pieces, right? Look over here to the right. Here's slip rings. You have two of them for an AC device, but in a DC device, you take the slip rings and you combine them into one ring, but you put an insulator behind them. So down here, as it rotates down through the field, we get one conduction here, but as it comes halfway around, this becomes a switch that automatically flips the polarity around. And whenever it flips around 180 degrees, now you're just taking this negative alternation and making it a positive alternation. You actually have, instead of continuous contact here, you have something called a commutator, which actually flips over the polarity every half turn of this winding. And when we do this, we put a commutator on this coil that is spinning around. This is a rotor with slip rings. If I put a commutator on there, as I see here, compared to slip rings with brushes, what we find out is that it becomes an armature. So an armature is actually a rotor that has commutators on it instead. So it's real easy to see here how when you rotate around, it flips the polarity. This is actually a mechanical switch. If you've ever seen a real DC motor running, it makes a lot of sparks, and that's why, because of the jumping between here and here. If you can actually look in there and see the spinning part of it, you can see it making sparks when it's spinning. So that's how we can take an alternator and make it into a generator. Or how can an alternator be made to generate DC instead of AC? Change the slip rings into a commutator. That's what you would do. 1 out of 100 questions, but now you know the answer. Okay, now when I look at the spinning portion here, down here at the bottom, if I look at the spinning portion rotates in the field. It's a little bit easier to see here. The coil comes down through this side, and then it goes back up through this side. So that's the positive alternation, the negative alternation. But in a basic alternator or a generator, the field, the magnetic field, is provided by a permanent magnet. Let's go back and look at that. Okay. Remember we said the two main parts were the spinning portion and the field. Well, the field is sometimes provided by a permanent magnet. It provides the magnetic field. And in a better type of device, that magnetic field will not be provided by a permanent magnet, but we're going to use some kind of electromagnet. So we created an electromagnet here. You might remember this from grade school, where you put a battery on a nail, and the nail picked up the paper clips. And over here you get a better feel for it. Here's the magnetic lines of flux, and here's an electromagnet. Now what's interesting about this is the magnetic field is not only provided by an electromagnet, but the amount of current or voltage applied to this coil controls the amount or strength of the magnetic field. And it stands to reason that the stronger magnetic field that this winding has to pass through down here, the rotor or the armature has to pass through, the more electricity it will generate. So the stronger the magnetic field, the more electricity it can generate. The weaker the magnetic field, the less electricity it will generate. Hey, and guess what? This is exactly how at a generating station, whether it's coal-fired or nuclear, that's how they control the amount of electricity coming out of the generator or out of the alternator. When they're spinning that alternator If it's in the middle of the night and they don't need a lot of electricity, they just turn back on the strength of the field. It generates less electricity. If during the day when everybody's getting home from work and all the ovens are turning on, electric ovens, electrical stoves, the air conditioner comes on, then they need more electricity. They make the field be a stronger field by adding current or voltage to the field. So, in review here, what is used to provide the magnetic field in an alternator? Typically, an electromagnet. How is the energy output of the generator controlled? By the strength of the field, by adding more or less voltage to this, more or less current to this electromagnet. More current makes a stronger magnet. More electricity comes out. Less current in this magnetic field will make less current come out of the generator. So the interesting thing about that is that when you generate AC, it's the speed of the rotor that generates the frequency. So typically a 60 hertz signal has to be rotated 60 times per second, or three-phase. It can be rotated slower, 20 times per second. Well, we're not going to get into that. So you can't change the speed. The way that you control the output of the generator is actually to control the strength in the field with different current in the field. Now finally, the last thing I want you to know about a DC motor or generator is sometimes op-amp circuits are used to control the speed of a DC motor. So let's take a look at that in the next slide here. And the way that we typically do it is we use a comparator circuit. Here's a comparator circuit right here. An op-amp comparator. What does a comparator do? It compares one voltage with the other. It gives you a high output or a low depending on how they compare. Generally, the speed of the motor in a control system, and probably you're covering this now with Mr. Kanjierski, is you know that in a feedback loop you could use control. You look at the amount of the feedback and compare it to a set point. My set point is here. My set point. This is a control, which will give me faster or slower motor speed. And back here is the feedback. This is the feedback of the monitoring circuit. This comparator is driving a set of FETs, controlling an FET here, a MOSFET it looks like, an EMOS as a matter of fact. And my motor is between here and here. So I'm controlling the amount of energy that is getting to the motor with this FET down here. Oh, I'm sorry. This is the 12 volts coming in. This is the motor right here. I apologize. This is the power coming in, the on and off switch for the circuit. This is the voltage going to the load. This is going to your motor here. That's where the motor is. So when this comparator sees a need to make the motor get more energy, it'll turn this FET on, and it'll send more power to this load. If the motor is going to speed up, and we don't want it to speed up, it'll turn this FET off. So the comparator is comparing something to a set point. That's why it's called a comparator. So back here, what type of op-amp circuit is typically used to automatically control the speed of a DC motor in a control system? Well, guess what? That would be a comparator. Okay, so much for motors. How about this odd stuff about the oscilloscope? Let's take a look at that. Now, up to this point, you've been told over and over there's two axes of an oscilloscope. Well, in reality, there's three of them. Yes, there is a horizontal and a vertical. But the three axes are the X, which is the horizontal in time, the Y, which is the vertical, which is what you typically see on the oscilloscope here, the X and the Y, the voltage and the time. And that would be your answers here, number 3, voltage and time. But you have another one. And the reason why you have another one is in the back of the scope, a beam originates which shines and hits the front of the screen. And so it's coming from the back of the CRT. I probably should have put a picture, but let me see if I can draw this for you real quick here. So if you look at the top of an oscilloscope, you notice it's a big, long box. And back here is where the beam originates, and the beam shoots up to the front, and hits the front of the screen right here. Well, this is tilted to the side. If I was to look at the front of the scope, which would be looking at it from the front side here, I would see this. But if I tilt the scope to the side, I could not see these axes, but I would be looking at the length of the O-scope here. Okay, now, that beam shining from the back to the front is your intensity control. That's what makes the brightness of the line on the front of your screen. So intensity and focus are typically thought of as being the Z-axis. So which axis is in the intensity and focus? It's the Z-axis. A weird question. I wonder if that's still on there. You know, I hate seeing questions on there that of things that we've never covered in class. Okay, so there's your answers. What are the three axes of the O-scope? X, Y, and Z. Which one's horizontal? That would be the X, it's the time. Which one's vertical? That's the volts, it's the Y. Okay? And which one is the intensity and focus? What's the beam coming from the third dimension? That is the intensity. That is the Z-axis. Very, very rare will you ever see on any kind of test, but it's one of them ones they want to fool you. Now, how many vertical inputs does a dual trace have? Well, look, dual trace. One here and one here. You might recognize the scope. Two inputs for vertical, here and here. In case you didn't know it, a dual trace oscilloscope actually uses one beam. First it draws this beam, that diagram, then it draws this one. So when you flip this into dual mode down here, you're actually using one beam very quickly to draw both of these. Now how many focus controls? These are vertical. That's what axis? Vertical is what? The X or the Y? Well, that's the Y. So it has two inputs, two controls, and two positioners for them, for the Y. How many focus controls, how many Z-axis controls does it have? It has one focus and one intensity because you're only using one beam to draw both. So you have those. How many sets of position controls do you have? Well, I've got one over here, well, we have one to move the beam back and forth, and I have another one right here to move it up and down. So I actually have two sets, a vertical position and a horizontal position. Okay, how many horizontal controls does a standard dual trace have? I only have one time per division, because the time for this is the same time for that. I'm not changing the time. They do make dual trace scopes that have two separate time controls, but that means it has to have two separate beams. They're much more expensive. Okay, how many vertical inputs do you have? Two vertical controls. How many focus controls? One. How many intensity? One, because there's only one beam. How many position controls for a dual trace? Two. How many horizontal controls does it have? One. Next. Okay, how about this stuff? Some odds and ends about diagnostic, repairs, and other test concepts that you should be familiar with. Well, they have an odd question that will appear on there because they know that you fix things. They want to make sure that you know how to use a soldering iron. First of all, look over here. You see anything wrong under this picture to the right here? Is there anything interesting about this over here? Is that the proper way to hold a soldering iron? I would imagine not. What's the problem with holding a soldering iron like that? Evidently, somebody who took this picture had no idea. Well, first of all, if you smell something burning and it smells like roasted chicken, you're probably handling the soldering iron the wrong way. And by the way, by the time you would smell it burning, it's probably you've already let go of it and thrown it down and got third-degree burns on your fingers. Okay, so that's not the proper way. But generally the questions revolve around how do you clean a dirty soldering iron tip? Well, first of all, you never use anything abrasive. I know sometimes you see them use steel wool or a pad. You do not want to say that on the CET. You never want to use sandpaper, steel wool, or anything like that. The reason is this is most likely a copper tip or some other metal, but around the outside of this tip it's tinned. If you use anything abrasive, it'll take that pin off of there. It'll ruin the tip. So generally, you want to wipe it after it heats up, and then re-tin it with some fresh solder, or use a sponge after it heats up and put in some flux and some solder. So you want to be very gentle with the tip of your soldering iron. The proper method, you generally want to wipe it after it heats up, maybe flux and put solder on it. You never want to use acid core flux, ever. Acid core flux will cause problem in electronics. Okay, so watch for that question. The key thing here is never use anything abrasive or sounding abrasive in that question. They'll try to fool you on that one. Okay. What precautions should you take when you're soldering high voltage connections? Interesting here. This question comes from the time of old TVs and modern oscilloscopes where you're using a CRT, the CRT that I described previously about the electron beam in the back. Now, it takes about 15 to 40,000 volts to generate that beam. And so, in the future, you may be required to solder a high voltage connection. Generally, any kind of point on the top of a high voltage connection, for example, if I make a soldering connection, and it has a point on it, and it's round like this, right here, at the point, I will tend to get electrons gathering. And high voltage will cause a lot of electrons. Electrons tend to gather at the point of something. And right here they're showing you the sharp tip will cause a lot of electrons to leak off of that through the air. Yes, eventually it'll arc and go to ground and cause a carbon track, which will cause the electricity to constantly flow to ground. I remember when we were in the TV fixing days, or in a computer monitor that uses CRT, a cathode ray tube, you would hear a hissing sound in the back. That was an indicator that something was pointy in there and causing an arc to begin. Now, one way to get rid of that problem, at first you won't get that, but over time you will get some carbon tracking and a corona discharge there, or plasma discharge, just like in a spark plug. That's why spark plugs are pointy on the end. Then what they'll tell you is, to get rid of that possibility of causing a corona or an arc, always make your solder connections round and flat and smooth. So whenever I do a soldering iron connection, a solder connection for a high voltage, I want to make it nice and smooth and round, trying to avoid any kind of points on there. That'll make it last a lot longer. A couple of weird questions you run into. Yes, they are odd. Now you know the answers if you run into them. Okay. Whenever I was in electronics school, and you're going to hear me talk about this all the time if I ever have me as a teacher, because we learned a lot of different things compared to what you guys are learning today. Back in the days of bear skins and stone knives, when I was an electronic technician, beginning just learning my material, we did not have digital readouts. We actually had a meter with a needle on it that moved back and forth like you see right here. So that's what an analog VOM is. And they'll ask you, sometimes you'll see the letters VOM, what the heck? You know, a lot of students will tell you a VOM, oh, that's a volt-ohm meter with a pointer on it. Well, not quite. It is a meter with a pointer on it, but V stands for volts, O stands for ohms, M stands for milliamp meter. So a VOM is not just a volt-ohm meter, it's a volt-ohm milliamp meter. That's what it stands for. Now, why are analog VOMs still periodically used in place of a DMM? Well, here's why. Have you ever looked at a DMM when the voltages or resistances are constantly changing? It's very hard to figure out what it is because the numbers turn so fast there. So these are difficult to tell if it's gradually increasing or gradually decreasing. On the other hand, if I have a pointer, I can actually see, like a speedometer, I can see the needle. I can tell if I'm accelerating or if I'm decelerating. Is it increasing or is it decreasing? A pointer makes it really easy to see varying voltages or fluctuating values. So a VOM is still used sometimes if I'm trying to tell if something's increasing or decreasing. It's hard to see that on a digital readout. Sometimes, if you're really good with it, you can tell. But other times, if it's changing too fast, you can't tell if it's increasing or decreasing. And so fluctuating signals are sometimes we still like to use VOMs to see fluctuating signals. Now, another issue with the VOM is down here, you have positive and negative inputs on a digital readout. All that happens if you hook the leads up backwards is you get a negative sign here. That doesn't damage the meter. But look over here. I have a stop to the left of this. I have a place where the needle stops. And what if I hook this up backwards, my red and the black lead, and apply a really high voltage? Well, it's not going to want to move this way, but it'll happen. The needle will want to move this way, and it can't move. It's up against the stop. It would be like trying to drive in reverse 100 miles per hour. And what will that do? That can possibly break this needle. And so, what precautions do you have to observe when connecting an analog VOM to a circuit? You have to watch the polarity because the needle only moves one way. Up here with the digital readout, all that happens is you get a negative sign. So what? Big deal. So you got to watch the polarity when you use a VOM. Now, I put this one off till last. Here it is. Why do DMMs typically use an LCD? Well, listen to this. Back in 1976, when they come out with the first digital multimeters, DMM, I was in school, and we had these kind of readouts. These are called LED readouts. The trouble with LED readouts are they need about 100 or 1,000 times the amount of current than an LCD does. And so the batteries would go dead quick with this. So watches or meters that use an LED readout aren't very efficient as far as battery power goes. So a little bit later, they developed another type of readout called an LCD, liquid crystal display. And LCD, liquid crystal display, needs much, much less current. They use LCDs on DMMs and watches today because it's a very, very low current device. How about that? It just happens to be the same letters. LCD stands for liquid crystal display, but some students think it stands for low current device. But no, an LCD uses only about 1/1000th or 1/100th the amount of current that we need to drive an LED. So that's why DMMs typically use an LCD. They're very, very efficient and very good with power and the extension of battery. Like they use very little current. It's a low current device, low current display. Okay, next. You might run into one or two questions about thermocouples. So let's just hit that right now. I would imagine whether you were in the gas and oil or whether you were on broad-based electronics, you studied thermocouples. Here's the idea behind a thermocouple. I'm going to just tremendously simplify it. If I twist two wires together of dissimilar metals, it naturally gives off a very, very tiny voltage, a voltage that's in the millivolt range, very, very tiny. Generally, if you're going to use this in a control system, you'll have to put some kind of amplifier on it to be used as feedback. But the output of a thermocouple is in the small millivolt range. I'm thinking like 1, 2, or 3 millivolts. Even that's pretty high for a thermocouple. Now, what we find is not only does it put out a voltage here that can be read with a voltmeter, but if I heat or cool this connection here where they're twisted together, it'll make this voltage change. It'll make the voltage change. And so we can use this as a control device. For example, inside of a hot water tank, you have what's called a pilot. The pilot is a very, very small flame that is used to ignite the main burner. So over here is the main burner, and the pilot would come out of here. And that pilot has to be lit to ignite the main burner over here. If this pilot gets blown out, for example, a windstorm comes and blows a little bit of air down into the chimney and blows his pilot out, that pilot's getting gas all the time. And that could cause a lot of unburned natural gas to gather on the floor of your cellar. And then somebody comes down and turns a switch on, or comes down and tries to ignite the pilot, and that will cause an explosion. So a thermocouple is used with that. That thermocouple is used to only allow gas to come out of that vent right there to be lit if heat is hitting this. This is why when you light a pilot lamp in a gas device, a natural gas device, you have to hold a button down for a while that pilot is lit. You light the pilot, and then this thermocouple here gets hot enough to generate a voltage to make a control system hold the valve open. And so that's why we use thermocouples. That's a really good spot for it. Gas furnace, gas water heater. It's used to indicate there is a flame there. There's a flame that will ignite that large burner whenever that burner turns on. You can imagine if there's no flame there and that burner turns on, you're really going to fill up your cellar or your area with natural gas. Okay, so that's what a thermocouple is. How does it work? It's two dissimilar metals. When you twist them together like this, it generates a voltage. It changes with heat. And the amount of voltage you get out of thermocouple is generally in the millivolt range. If you see a thermocouple on there, probably just 1 or 2 questions, and that's it. And if you think about it, 1 or 2 questions out of 100 is only 1%. You don't even have to know about it, but try to hit these odds and ends that, they make up about 5% of the test. But that 5% could be the one that actually allows you to pass or not. You get a 75 or a 76, you pass. You get a 74, you do not pass. And there's no review you cannot go in there and say, well, this is an unfair question. These are made by other people. This is a third party. PTC has nothing to do with the creation of the questions on the CET. That's why we've been talking about the different language that you're going to run into. From the beginning I've told you, these are made by old seasoned professionals that have been in the business for a long, long time. They're purposely going to give you answers that sound good, and you cannot come back and say, hey, that question, it's a tricky question. Well, duh, it is a quick tricky question to see if you can think through it or not. Okay, you're going to run into this word, signal injection. Well, what is signal injection? Anytime you take a signal generator and feed its wave shape into a circuit here, here's a circuit on the bench, that technically is called signal injection. So, signal injection is using some kind of oscillator, typically in the form of a generator, audio, signal, function. There's different names for generators. And we're going to use that signal for testing purposes. You've done this through your whole stay at PTI. You've used a generator, the Inspec, the audio, the RF generator. They're all types of generators. When you use that generator, put a signal or a wave shape into a circuit here, that's called signal injection. Now, sometimes they call out for you to use a coupling cap on a signal generator. Those of you that build the AM radio or wireless receiver project, you remember they made you use a coupling cap there. The reason why we have to use a coupling cap is sometimes the circuitry in the generator or the signal injection device can cause a little bit of loading over here in the circuit. And so using a coupling cap blocks any kind of DC that might be from the generator that might get into this circuit. You know that these transistors have a DC bias on them. If there's a DC voltage, even slight here, that gets into there, it can cause the circuit not to work right. So by using a coupling cap, we can use the AC coming out of the generator without worrying about the DC that's in the device that's making the wave shape. Generators should not do that, but a lot of them do, and there's nothing we can do about it. So just to make sure, you might recall this from the AM Wireless project. This is a picture I cut out of the book and put on here. there was a coupling cap, a 0.02 microfarad. You might even remember for the audio generator, you needed a 10 microfarad cap. So coupling caps on the output of a generator generally make it work better by keeping the generator from loading the circuit. Okay, they're going to ask you, do you know what a logic pulsar is? All right, let me give you the answer to that right now. A logic pulsar is a digital signal generator. Generally, it's designed to be held in your hand. What I believe you are familiar with is a simple logic probe. A simple logic probe right here, a simple logic probe like you see here, all it does is read the highs and lows in your circuit. Well, before you guys came along, we used to give you something called a logic pulsar in your kit. A logic pulsar is a logic probe and a generator in one. I can actually use this to inject the signal into a digital gate. And then I could use the probe to watch what's happening on the output. So what is a logic pulsar? It's a function generator that generates digital logic on its output. Simple highs and lows. I press a button on here, and coming out of this will be digital pulses or rectangular wave shapes coming out that I can use to trigger logic gates. It's very, very handy. Instead of just getting a generator, which is big and bulky, I can just hold this thing in my hand. Now this one has a logic pulsar and a logic probe, so just by pressing the switch back here someplace, I can convert it into a generator or into a probe. So a probe reads logic states. A logic pulsar can inject digital signals into digital logic. Typically, it's thought of as a square wave generator of sorts. So many times you can buy two devices in one. I don't know why PTI doesn't give that to you. It's only like a couple of bucks more. So, you know, you can push a button over here to actually inject the signal. Typically, a logic pulsar has to get its positive voltage from someplace in the circuit. I believe that these also do as well. Okay, let's think about troubleshooting. There are a couple of troubleshooting questions in there that see if you can logically figure your way through. These are a couple of ways that I actually look at troubleshooting. You know, look over here. Does it work? Yes. Don't mess with it. You're done. Okay? Does it work? No. Did I fool with it? Yes. Well, you shouldn't have. You shouldn't have fooled with it. Does anybody know? No. Hide it or throw it away. Okay. Did you fool with it? Yes, and it still don't work. Does anybody know? Yeah, your boss saw you. Well, look here. You're in trouble. Can you blame somebody else? No. So you're stuck in this loop here. No. Here, did you fool with it? No. Will you get in trouble if you don't fix it? Yes. You don't know how to fix it? You're in trouble. You're stuck in the endless loop. Okay. Will you get in trouble if you did you mess with it and it don't work? Well, no. Then just throw it away and nobody will know that there was a problem. And then the boss can try to figure out what's going on. In actuality, we like to think that would be a simplistic form of it all, but really it is not that simple. Let's talk about some simple troubleshooting. Of course, I'm just joking around with this. I'm sure that you've probably seen this if you've worked in troubleshooting. This is a very, very popular troubleshooting chart. Sometimes there was more cuss words in here. I kind of left the one out that has cuss words in it so that you would not be offended. All right. Here's a typical question that you might see. A consumer electronics boombox device, of course boomboxers are old, but a boombox device, you might remember some kids carry them on their shoulder and play the music really loud. Or you can have one at home. It's a multiple device. Boombox is just kind of a word that we use. It's probably politically incorrect today, but there you have it. And it has an audio amp. It has multiple devices. It has a CD player, an iPod dock, an MP3, a radio, among other gadgets. And it's all controlled by a selector switch. So you have a speaker, an audio amp for volume and tone, and a selector switch which selects these different devices. So in your mind, you kind of have to think about this block diagram. As a teacher, I promote the idea of looking at a system as a block diagram. Hopefully your teachers taught you the same thing. Block diagrams make it easy to troubleshoot. Now here's how this device works. First of all, look, I have one power supply. Powers all devices. I have one audio amp that drives the speaker. The audio amp gets its inputs from all these different devices. So all these different devices provide a low-level signal into a switch which selects what I want to listen to. For example, if I want to hear the radio, I put the selector switch in radio. If I want to hear the MP3, I put the selector switch in MP3. If I want to hear the CD player, I put the selector switch in CD. Yeah, CDs are going by the wayside, but that's not going to stop it from appearing on the test. So depending on what I want to listen to, there might even be a separate AM and FM radio where I have to switch back and forth. So the concept here is one audio amp, one power supply powering everything, and a speaker. And to get the different devices to work, I use a selector switch. And these devices will send out some low-level audio into that switch. Depending on where I have the switch on, that's what's going to be amplified. That's what I'm going to hear out of the speaker. So that's your basic idea behind that. So first of all, they're going to see if you have a rough idea of how block diagrams are arranged. Now, here's the same question. There are two likely reasons, and they might ask you this question about audio hum. What does hum sound like when it comes out of the speaker? Have you ever heard that? It sounds like this. Generally, it's about 60 or 120 hertz. Where's that coming from? Well, it's coming from the AC outlet that gets into your audio amp. If it's not filtering properly, you're going to get a full wave hum, which will sound like 120 hertz, or a half wave hum that'll sound like 60. So they sound very similar, even though they're both very, very low and double the frequency. So what are the two likely problems that would cause a terrible low frequency hum in the audio products? Well, I'll tell you. Okay, let me see if I can draw here. First of all, note that all of these are powered by one power supply. And if it's a full wave or a half wave, the power supply is generating these positive pulses here. And that's coming out of the rectifier. We need capacitors here to bridge this together, so you don't get a lot of ripple in that output voltage. Now, if the capacitor goes bad, if the cap goes bad in the power supply, there'll be no bridging action here. And what you'll hear is a signal that sounds like this, a hum at the frequency of the rectifiers. That's the ripple frequency. It won't look exactly like a sine wave, but it'll hum like a sine wave. So, one of the things that will cause a hum in this product, if it's not being powered by batteries, because if it's being powered by batteries, you won't get the hum. But if it's not being powered by batteries, and I have it plugged into the wall, and the power supply is bad, I'm going to get a terrible AC hum that sounds like this. Okay. Now, the interesting thing about that is, if you have a power supply that's causing the hum, all these devices are powered by the power supply. So no matter where I put the selector switch in, what position, that audio amp and these devices will be humming. So one likely cause is a bad capacitor in a power supply, filter cap. If that goes bad, I'm going to get the hum no matter what position the selector switch is in, primarily because this audio amp is powered by this power supply, and if that power supply is humming, I'm going to get the hum in the audio amp. That will be amplified and go to the speaker. Now, another cause is a bad shielded cable. And shielded cables have a shield around them, and there's a conductor in the center. And here's a shield. And the shield is connected on the outside if it's using a coaxial cable connected on the outside. It's very, very common for these cables to have the shield disconnect from the connector. It's very common. A little bit of wiggling can make this shield break off. And if that shield breaks off, those cables are right in here. If that shield breaks off, it'll also generate a 60-cycle hum. Why? Because once the shield breaks off, I am going to allow the 60-cycle radiation that is in the air to get onto that semiconductor. Right now, all around you is 60-cycle wireless noise. In electronics communication, you probably learned about noise, hopefully. And if I don't have proper shielding, the noise will get in to the audio or into the data and cause that noise to be amplified by the amplifiers. So, if I have a bad cable in here with a bad shield or just a bad cable, I will get hum. But the interesting thing about this is it will only hum on the particular setting. For example, if these three cables are good and this one is a bad cable here, it will only hum when I put it in the CD position. Or if the radio only hums. These three will work, but it will only hum in the radio position. So I can have a bad shield on a cable or a faulty or intermittent cable, audio cable. And if that happens, typically it will only hum on one particular setting. Now what you want to watch for is that this is actually connected to ground. I see that. Shields are typically connected to ground. But don't be fooled by the question because they're going to say a bad ground in the audio amp. Well, no, the bad ground is back here. But it's a faulty cable. Don't think of it as being a ground. It's just that you have a bad connection on the shield from here to here someplace. So watch out for that distractor about the ground. That looks like a good answer, but it possibly is not. Okay, so here's the same question. Look at the question here. If the hum occurred as soon as you turned it on, no matter what the selector switch was set to, what most likely would be the problem? Well, after that discussion, what do you think it is? Well, it'd probably be the filter cap, right? Because the filter cap is powering the audio up in all the devices. Okay, so how about this one? If the hum only occurred when the selector switch was set to a particular setting, such as it only hummed when you put it on CD, what would be the problem? Well, probably the cable or connection is bad between here and here. It would not be about bad ground in the audio amp. There's something wrong with this cable, bad ground on the cable, but they're probably going to ask you about the shield. They'll have that ground in there as a distractor, I would imagine. Okay, last but not least, I wanted to talk with you about square waves, and I'm hoping in your communications class that you did learn about using square waves as test signals, whether you're in gas and oil, or whether you are in the broad-based electronics program, or even in the smart building technology classes. You should have learned about square waves. Square waves make an ideal test wave to check frequency performance or response of circuits to tell if they're working good or not. And here's why. If you haven't learned this already, it'll be surprising to you. There's only one kind of wave in the world, and that's a sine wave-shaped wave. All other wave shapes are created by adding together different frequencies of sine waves. For example, a square wave here, what you see on the O-scope, square wave, actually is made up of a fundamental or a base frequency of that square wave and all the odd order harmonics. Harmonics are multiples. Odd order means multiples of the odd number. So if you look here, here's a 60 hertz, we'll say this is a 60 hertz square wave right here, what we're looking at, the red one. If it's 60 hertz, I'm going to have the first harmonic, which is 60, the third, the fifth, the seventh, the ninth, the 11th, 13, and so on, all the way out through infinity. These represent the power of the sine waves of those different frequencies. They're all on-order harmonics. So square waves make an ideal wave to test a circuit, because theoretically a square wave has all frequencies out through infinity inside of it. That's why it's a great testing wave. Now the interesting thing about this is that if I have a circuit with a very, very good frequency response, all of the wave passes through. That means it passes all of the harmonics. I put a square wave in, and I get a square wave out. Right here, a perfect square wave on the output means the circuit is passing all frequencies equally, and it's working perfectly for its frequency applications. This wave shape indicates a well-balanced circuit that is performing great. So I put a square wave in on channel 1, on channel 2 on the scope. I look at the square wave coming out. If I'm getting a pretty good square wave, I know that circuit is working very, very well. Now, here's an interesting, here, check it out. They have a little, they're showing you here that a square wave is actually made up of all these harmonics added together. Now, if I have a circuit that is knocking off high frequencies, if I have a circuit that's knocking off high frequencies, it'll be rounded on the outside of the wave because the lower frequencies are beefing up the center. So rounding on the outside of the wave is an indicator over here that a square wave that is distorted here, that's rounding on the sharp corners, means it's lacking the higher frequencies. Okay, that's what's wrong with it. So if I put a square wave in, and I get a rounded, almost sine wave coming out, that means it's lacking the other high frequencies that make up the sharp edges. In a square wave, the sharp edges are made by the higher frequency harmonics. And if you think about it, look, if I draw this wave, look, here's a sine wave and here's a square wave that'll be made from it. Think about it. This is starting to look like a sine wave, isn't it? It has a lot of the lower frequency power in it, the first harmonic. It's got a lot of low frequency power, but very, very high frequency power that creates the sharp edges. Okay. Now, an opposite on the high end, if I'm lacking high frequencies, I'm going to get a rounded edge. But if I'm lacking low frequencies, I don't have anything in here to boost this up to make it square right here. Okay, so the low frequencies have to be present to create the middle of that wave. So the high frequencies produce the edges, the low frequencies produce the middle. And if I have it lacking here in the middle right here, I am lacking low frequencies from getting into that output here. So if I put this wave into a circuit and I get that wave out, I'm lacking low frequencies here. So up here, generally a square wave that is distorted as you see here is an indication that the high frequencies have been amplified more than the lower frequencies. And this may be caused either by too much high frequency or too little low frequencies passing through that circuit. So there'll be a couple of questions here. Let's take a look at them. Here we have a high-pass filter. And first of all, why are square waves a good indicator of frequency response? Well, the reason is square waves actually contain thousands and thousands of sine waves of different frequencies. That's why. Now, here's a high-pass filter. You'll recall from second quarter and maybe some other class, the high-pass filter is an L network with a capacitor in the top. That's a high-pass filter. Do you see this is a high-pass filter? Input through the cap to the output. Input through the cap to the output. Resistor from the output to common. Resistor from the output to common. This and this is the same circuit. You're going to have to get used to seeing circuits drawn differently. Not everything is drawn textbook in life. Okay, now if I put a square wave into this circuit right here, and I get this wave shape out, I put this in, and I get this out. From what we just discussed, what is lacking? I put this in, and I get that wave out. What is lacking? What does this tell us here? Well, we have low frequency attenuation. The low frequencies are not working well. The low frequencies aren't getting through the circuit. Okay. Now, here's the cutoff frequency right here. Frequencies below this cutoff point, this is a high-pass filter, and that's a high-pass filter, high-pass filter frequency response. I need to get more of these low frequencies to pass through. So I have to move this cutoff point down here somehow. So if I move this cutoff point down here, I could get more of these low frequencies to pass through, and the wave will look more like it should look instead of like that. So let me just see if I can draw this on here. If I can extend that cutoff point down like this and make my cutoff frequency right here and make this cutoff point down here, I can let more of these low frequencies that are in that area in here pass through, because right here these are being stopped. That's apparently the frequency of cutoff. Now, what is the formula to determine the frequency of cutoff for a high-pass filter? Well, the cutoff frequency is determined by 1 over 2 pi RC. Look at this. This is a fraction. And I have these values of R and C. I need to make this a smaller number to let more of these frequencies that are below the current cutoff come through. What can I do to R or C to make this a smaller number? This is in the denominator. And so, how can I make this number smaller? What can I do to the denominator? Well, if you had me from math class, you know we talked about this. You would make the denominator values bigger. So what can I do to the values of this filter? I can either make R or C bigger. Making R or C bigger will make this cutoff frequency be lower, and it will tend to smooth out the peaks of this wave up here. I can make it more like a square wave. This part here and this part here is what's missing. It's the low frequencies. It might not be perfect, but I can make it better. So, what can I do? What can be done to the components of a high-pass filter to make the square wave pass through the circuit more faithfully? Faithfully meaning it's going to pass through better. Kind of an odd word there, I know. Well, I can increase the value of R or the value of C. Increasing R or C will lower the cutoff frequency. And there you have it. Well, here you are. The last practice quiz. And then you'll have to take a bunch of practice tests. So let's get on with this practice quiz. Get your notes together. Let's digest what we just covered. All these odds and ends, weird things that you normally don't see in class. Sometimes you do, sometimes you don't. Let's talk about the quiz. Okay, in a generator, a DC voltage applied to the field windings can control the output level of the generator. Is this true or false? What do you think? True or false? Well, we said that the field is usually an electromagnet, and the strength of the field can make the output of the generator change. And so, if you apply voltage to the field of the windings, I can control the output level, different voltage. So I'm going to say the answer for that one is true. Okay. Oh, no, this isn't fair. I just covered this. Okay, in the circuit below, to reproduce the square wave input more faithfully at the output, what can I do? Well, looking at this output, I can see it's lacking low frequency response. So I see this is a high-pass filter. And over here is the frequency of cutoff. And if I want to make the lower frequencies come through this better, I better increase the denominator values, which will make this get smaller. This will make more low frequencies pass through. So I can't change 2 and I can't change pi. The only thing I could do is increase R or increase C, or both of them. So if I increase the value of this or that, I will make a better wave come out. So what can I do here? Decrease the value of the resistor? No. Lower the frequency of the square wave? No, that'll make it worse. Decrease the value of the capacitor? No. Decreasing R or C here will make F go up. I need more low frequencies passing through, not less. So what's the only possible answer here? Decrease the value of the resistor. That's the only possible answer. Increase the value of the resistor. Increase the value of the resistor is the only possible answer. Now you might see one that says increase the value of the cap, and you would answer that one. Okay. What is a logic pulsar? A logic pulsar can be used as a, well, what can it be used as? Let's think about this. Can it be used as a filter? No. Can it be used as a signal tracer? No, that would be a logic probe. Can it be used as a logic probe? No, logic probes have signals going in. A logic pulsar has signals coming out. What's the only possible answer here? That would be a good answer. That would be a digital signal generator. That would be your only possible answer. All right, here's a good one. Look, these are dead on what we've just talked about. A stereo amp has a severe hum. Whether CD, auxiliary, FM, or AM radio are selected. What most likely is the problem? Do you remember this answer? What most likely is the problem here? The volume control is shorted. The power cord polarity is wrong. You know, back in the old days, before they had a ground lug, that could have possibly been it. It's a defective output transistor grounding. No, it's not. The only possible answer is the power supply filtering is probably bad. That's probably what the cause is. Why? Because all of the devices are connected to the power supply. All right, what is the y-axis of the oscilloscope? What is the y-axis of your oscilloscope? Is it the brightness, the intensity, the focus, or the vertical? Well, intensity and brightness are virtually the same thing. And focus, we know all three of these are part of the z-axis, A, B, and C. The only possible answer here is going to be vertical. Now, it might say voltage as well. It might say time, division, or voltage, or horizontal, and you have to just pick the best answer for those questions. Only good answer here is vertical. A dual trace oscope does it have two focus controls? I'm going to say no. Okay, does it possibly have two sets of position controls? Well, I think that it does, doesn't it? Not only does it have one above channel 1 and one above channel 2, there's also a horizontal position control in the far upper corner. All right, so that's a possible good answer. What about vertical inputs? Well, dual trace oscope has two channels. Of course it has two vertical inputs. Now watch for these. You want to be careful that you read every possible answer. Because look, this one, not only is this and this right, but this is also correct. So that's why I always tell you, read all of the answers, pick the best possible answer. This is a good example. All right, when soldering high voltage connections, let's see, did we remember not to answer things that you never heard of before? That's a bad answer. It's important to use a thermal shunt. Well, it depends. Is it semiconductor or not? I don't know. Leave a wick in place? No, that wick actually will generate a spark off of a high voltage connection. Use minimum solder? No, that'll make it rough and pointy on the edges. The only possible answer here would be what? B. B is the only possible answer. All right, what should you use to clean a plated soldering iron tip? Well, what did we say? Nothing corrosive, right? So not coarse emery cloth, not acid core. That's corrosive, and a file is very corrosive. It lets you take metal off. There's only one good answer here. What is the only good answer here? Well, the only good answer is you can, when you get it hot, you put some flux on it, then cloth after cleaning. Wet or dry cloth, typically. I know they teach you wet, but dry cloth is okay as well. Oh no, not another one of these. A square wave question. Okay. In the circuit below, the output signal is not a true representation of the input square wave. What is wrong with it? Now, we've talked about this. When we look at this right here, here's the input, it's a nice square wave, and the output is what? What is this missing here? Well, it's missing that little loop there, that little curve. We said that would be that it's lacking low frequencies, or the high frequencies are too big. So we have a lot of low frequencies missing. The low frequencies are attenuated there. So what would be going on here? Is it clipping? No, clipping generates high frequencies, but it's flat on top of its clipping. Signal doubling? I don't even know what the heck they're talking about there. Is it a poor high-frequency response? No, it's pointed on the end. We have a lot of high frequencies passing through. The only possible answer here would be what? What is it lacking? It's lacking low frequencies. We have poor low-frequency response. This, by the way, represents an amplifier, not a NOR gate, in case you're curious. Okay. This was your last real CET theory. I'd like you to complete the quiz by Monday. And if you let me know right away how you want to get the practice tests, I'll get them to you. I can give you a hard copy. You can get them off of the Blackboard site. Or if you let me know right away, I can mail them to you. But you need to understand that if you're thinking about taking the CET, do not use notes or the answer key to complete this practice CET. The percentage you get right has to be above 75 or 80%. Otherwise, I would tell you, unless you're going to really study and make up for what you haven't done all quarter, not to waste your $60. You need a 75% to pass. What they'll tell you is, if you get all the easy ones right, you will get 75%. But you don't want to be at 75. You want to make sure you're going to pass. You want to get an 80 or an 85%. You want to be above, because if you miss a couple of those easy ones, boy, you're going to be very disappointed that you wasted your $60. On the other hand, if you get 75 or above, you become a certified electronic technician as recognized by the Electronics Technician Association. And you can put that on your resume. It looks so good to be a CET. Even after your name, you can put in there, Mr. Blah, 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 comma, CET in capital letters. Boy, that just looks so good whenever you're dealing with professionals. So the two practice tests, which are just like the CET, they're 60 questions each, and you should score a 75 or above on each one. If you think that you can do this, then I will move on and have you take the actual CET exam. And I'm thinking right now we're shooting for Tuesday right here, the 27th. That's the day that we're shooting for. If there's a problem for that, let's go with Thursday, the 22nd or 29th. Let me know if it's a problem with the 27th. Otherwise, I'm going to start planning for that. And let me know how you want to get the practice CET test, through the Blackboard site, or mail it to you, or just come in and pick it up behind my desk. Let me know so I can put your name on it. Or you guys that are in the broad-based electronics, just I can just give it to Mr. Konjierski and he can have it. I'd like to get that to you as soon as possible. We'll look at the schedules, and maybe I'll work on it this week, possibly. I think you guys have class tomorrow night, don't you? I could possibly just get that to Konjierski and distribute to you tomorrow night, those of you that are in the broad-based program that are still in controls. I bet you're working on relay ladder logic right now, I bet. Relay ladder logic and relays and PLCs and those kind of things. I've taught that class before. I'm quite familiar with it. Okay, so you need to keep in touch with me about Tuesday the 27th and about how to get the CET exam. I'll turn on that test by Thursday or Friday, get it out of the way. And what you'll do is I'll have the answer keys for you for the practice. Again, do not use the answer key or your notes to take the test. You want to use this as a gauge as to whether or not you're going to pass the CET exam. Experience shows if you get an 80 or above, you're almost certain you're going to pass it. 75, I'd be a little bit nervous. I'd study some more. And again, this should become part of your test bank. Cross off the answers you got right, circle the ones that you got wrong, and study the ones you got wrong. You should have a beautiful test bank now of practice and real quiz questions. Use those to study and prepare for the certification exam. Okay, other than that, I don't think there's anything else here that we need to see, is there? No, that's it. So I'm done with you. And what I want to say, if you've watched these, I commend you, because that's been a really difficult thing to do. I know that watching videos is difficult sometimes. So thank you very much for participating all quarter and showing your interest with that you really do want to learn. And even if you aren't going to take the CET, it's just a really good thing to have reviewed all this. So in case you get quizzed when you have input quizzes for jobs, you want to make sure that when the opportunity of a lifetime for your dream job comes along, that you actually can show that you know a little bit about electronics. And by the way, even if you don't know technical questions in an interview, never say you don't know. Say, wow, it's been a while since I've done this, and we did cover the material. And if you give me a chance, I know where to find the answer. So you want to don't just give up on a question, but say something like that, and that will really make you look good in the eyes of the interviewer. Okay, please keep in touch with me with the email. And other than that, I'm going to let you go. Thanks again, and good night, good morning, or good evening, or good afternoon, whenever you watch this show. Thank you.